My name is Qingyan. I am the director of PUI Academy for Interdisciplinary Research, and I have a great pleasure to introduce our seminar speaker this afternoon, who is Professor David PUI. Professor PUI is a regent professor at the University of Minnesota. When I was a PhD student, and I already know him at that time, of course, he doesn't know me. He was already very famous in the 1980s. And we work in a very close area, but not in the exact same field. So I didn't get a chance to meet him until 2 years ago when he had a meeting here in Hong Kong. And he was very enthusiastic to help PUI, and therefore now he becomes a very important person at the PUI. He's the PUI International Advisory Committee member, and also a PUI Senior Fellow. You know, as a PUI Senior Fellow, you need to reach to a very high status, and the university will grant that title. So Professor PUI also is the supervisor of Professor Zhang, the president of Hong Kong University. And you can see the achievement there. So Professor PUI has been working in the different fields, especially in aerosol science and nanoparticles. So that's the topic he's going to talk today. So actually, in the field, Professor PUI focuses on the particle instrumentation and the filtration solutions for air pollution control, industrial applications, and research advancement. So you might not know too much about the details of filtrations and particles, but I believe everyone knows PM 2.5, right? And the PM 2.5 is proposed by Professor PUI. And he has developed very many commercial aerosol instruments for PM 2.5 measurement. Just a few minutes ago, I was talking to him. I'm going to buy 2 more units of aerosol measurement equipment. Each will cost me over $50,000 US. It's a very expensive equipment. And he also invented the very large scale urban air cleaning systems. It's very known as the solar assisted large scale cleaning systems, which was installed in Xi'an, which I believe can clean the air for an area of 1 square kilometers at least. It's very impressive. So that's also known as the air purification towers. And now it's also being installed in Delhi, India. So Professor PUI is also a member of the U.S. and National Academy of Engineering, and also the academicians of the Academia Sinica in Taiwan. So he has published over 370 journal papers and has 43 patents, and also received many important and prestigious awards in the field. And also, Professor PUI served as a president for the national and international professional associations, including the American Association for Aerosol Research and the International Aerosol Research Assembly. So without further ado, ladies and gentlemen, please join me in welcoming Professor David PUI.
Thank you very much, Professor Chen, for your kind introduction. So I'm very pleased to come and visit PolyU again. Last year, I was on sabbatical at Hong Kong U and City U, and I did have a chance to visit Professor Yang and Professor Yang Cheng, and also give a talk last year. So today I'm going to give a different topic, and you may see a few slides that you saw last year, and I'm very happy to see some of the Hong Kong U students that I taught last year that are in the audience here. So today, my talk is on nanoparticle technologies in microelectronics, air quality, health effects, and filtration. And now I should right away mention that I'm director for the particle technology for many years, 30, 40 years. And we develop a lot of instruments at the particle technology laboratory, including some of this that I developed together with my student, Darren Chen. And these are the instruments that measure atmospheric PM 2.5 nano-sized particle in the atmosphere. I'll tell you more about that. And they have been used, there are thousands of this instrument around the world to measure air pollution in the atmosphere, and also used for determining the contamination in a semiconductor manufacturing facility. Now, since we develop a lot of instruments, so we need to calibrate the instrument. So we have actually developed quite a few techniques like particle size distribution, particle number concentration measurement and calibration, and those become ISO standards. And the third ISO standard, we did it together with my former student, ETH Professor Jing Huang, and we developed test method to evaluate the efficiency of air filtration media against a nanoparticle. Furthermore, for calibration, you need to have a defined particle size to calibrate your instrument. So I work with the National Institute of Standards and Technology. We make use of the technique I developed to certify 60 nanometer and 100 nanometer particle standard. So those are traceable standard to the 1 meter stick maintained at NIST. Now, I like to say that we treat the whole universe as particles, from stars, and here, this is a particle size distribution. This is the planet size distribution. This is lunar fine dust size distribution. This is atmospheric size distribution. And we do quantum dots and nanoparticles, and then quantum phenomena. So I'm very pleased that as a result of that, we have a student who has a very broad view. And in particular, we also partner with many industry. We have two centers. The first one is for semiconductor manufacturing with 17 member companies. And then the second one, Center for Filtration Research, is still very active with 18 companies. And from semiconductor, we have 25 PhD, and for filtration, 33 PhD students. And when they graduate, they actually go to work for those companies, and many go to the university. So therefore, I like to show you just a few of my students. Qingyan Cai, Chair Professor at Jiao Tong University in Taiwan, and Darren Chen, Chair Professor at Virginia Commonwealth University, and Zhang Xiang, President of University of Hong Kong, and Shongki Che, Yang Yi, they are in the semiconductor companies, and Jing Huang, ETH Zurich Professor, and Sei Jing Yok, a professor at Hanyang University, Korea. Actually, there are 8 professors in Korea, different university, that were my former students. And then Shintaro Sato, I want to, he's a Japanese student. I want to show you. He actually is now Senior Vice President and Head of Quantum Laboratory they have 2 weeks ago announced the world-leading 256 qubit superconducting quantum computer. So IBM CEO like to say that quantum is the next big thing after AI. But then Shintaro, I invited him to give a seminar at University of Minnesota last month. And he said that he need to modify that. It should be like quantum is the next big thing helping AI, because AI use so much computer time, and quantum computer can go many, many times faster than supercomputing computer. So now this is, and right now there are 3 companies that are leading the quantum computer. One is Fujitsu, Japan company, and the other one is IBM. The third one is Google. Now, after the announcement, guess what? You probably recognize Japan Prime Minister Ishiba. He actually went to visit Shintaro Sato, my student, and he's explaining the quantum computer details to him. And another student, Dr. Shunki Che, after he graduated, he worked at Samsung Electronics, manager, vice president, senior vice president, Samsung Display senior vice president, and LGE senior vice president. So he just recently retired. So I recruited him to come back and teach a short course. I will show you that later. Now today's talk, I will address nanoparticles, a multidisciplinary science and technology. Actually, some 30 years ago, I guest edited a special issue at the Journal of Aerosol Science. The title is Nanometer Particles, a New Frontier for Multidisciplinary Research. Guess what? At that time, nanoparticle word has not yet been coined. I noticed that after the special issue, people call it nanoparticles. And there are 17 papers in this special issue. So today, I want to address this multidisciplinary nanoparticle in 3 areas: microelectronics, air quality, health effects, and filtration. First, I'd like to talk about semiconductor manufacturing. Now, many of you may know that the lithography is very important. A typical conventional optical lithography is to shine a light through a, this is a silica substrate, the photomask, and then there are image etched on the photomask. So the light source will focus the image onto the wafer where semiconductor chips are being etched on the wafer standard. So now this is, for this optical lithography, you can have a pellicle to protect the sensitive surface. And so if there's a particle, contaminant particle coming in, it will be stopped by the pellicle, which is out of focus from the image. However, for extreme UV lithography with 13.4 nanometer EUV light, you cannot use a pellicle because the material will be absorbing the EUV light. So they need to do it without a pellicle, so that if there's a particle going into okay, so it's supposed to be flying in, and Let me see if I can do it again. Yeah, okay. So then it is in the same plane as the feature. So now if you print the chips, that defect will be on every chip. So you have to throw away those chips. So we need to develop method to protect against all the particle. At that time, about 20 nanometer, but now it's 10 nanometer, because this is the last top-down technology for making chips. Now, the protection scheme we developed, we were sponsored by Intel for 3 years. And I should mention that EUVL is still a hot topic. In fact, there are annual meetings on EUVL around the world. And at that time, Intel wanted us to develop technique to prevent particle contamination. So here is a mass sitting in a container with the feature size facing up. Now, any particle in here can settle on the mask. And so we propose to put a cover plate on top of it so that settling will be on the cover plate instead of on the mask. And furthermore, we propose to turn it upside down so that you do the EUVL beam by reflection and then with the cover plate. And then you can apply electric field to repel the charged particle. But that's not good, because if you have any charged particle that have opposite polarity as the mass surface, it will actually attract particle to the mass surface. So we make use of temperature gradient to push the particle down. And so you can also surround the mass by a particle trap, in which case you can use electric field also to reject the particle. So now the reason that temperature gradient works is because let's say that we have a top side that's hot and bottom side is cold, and here's a particle sitting. And in the gas molecule above in the hot side has a high mean thermal speed, and versus low mean thermal speed on the bottom side, so that as the gas molecule colliding on the particle, it will push the particle from hot to cold gradient. So this is thermophoresis. I should mention that for semiconductor manufacturing, a lot of technique is made inside a vacuum chamber for plasma etching, for CVD deposition. They are all operating at the millitole level, so that there are not that many gas molecules. So we like to implement that in this rarefied environment. So this is what we start out with. We have to mount the mass upside down inside this vacuum chamber. The vacuum chamber has a turbo pump pumping it down to nano millitole level. And then here's the cover plate, but then we put a hole in the middle, and we design a injector to shoot particles all the way to the top. And some went through the pinhole, and we make it stop at the interval between the mass and the cover plate. And this is very challenging, because how do you shoot particle into a high vacuum with known velocity? But we were able to do that. And so we look at two situations. First is that we put the particle into the gap, and then with no temperature gradient, you see that the particles stop, and then they start diffusing to the top surface because of the for vacuum condition, the mean free path of the gas molecule is very long. So the particle tend to diffuse very rapidly. And then if we just put a 10 Kelvin per centimeter of temperature gradient, like 10 degrees C difference between the top and the bottom, you see that it's very effective, pushing all the particle to the cover plate. And so this is the apparatus. The vacuum chamber is in here. And then this is the injector that we inject the particle in here. And this is the turbo pump that we pump the chamber into millitol pressure. And then this is the chamber. And you see this cover plate with a pinhole. What we do is to mount the mass here, and then we flip this plate upside down and plug onto the cover of this vacuum chamber. So then we have this set up. Now, we also do detailed modeling. So this is particle speed as a particle size, and we can model that this curve is with 0 degree temperature gradient, and the dotted curve is 10 degree per centimeter temperature gradient. Now, all the points above the curve, particle will be deposited. All the points below the curve will not be deposited. So we first shoot particle in the upper region. We know that particle will be impacted on the photomass. And you see that in the case of no temperature gradient on the left-hand side, not only there are impaction, but also diffusion all over the, we call it the witness plate. We make use of a wafer in this case so that we can scan it quickly to get the results. And in the case of 10 degree Kelvin per centimeter, we still have impaction because this is on top of the curve, but then all the diffusing particles disappear. So next, we put 2 points in between the two dash and the solid line. And then you see that in this case, we have almost no deposition because this, and then in the case of 0 degree Kelvin, we do have particle deposition. But then if we have a temperature gradient, just 10 degrees C per centimeter difference, no particle deposition. So what happened is that, okay, next we have points below the curve. So there's definitely no deposition. So I should mention that many years ago, we have already developed this thermophoresis technique for the semiconductor manufacturing. And I understand that this has been a common practice now in all the EUVL system. Okay, so next topic that I like to address is air quality, PM 2.5, respirators, urban cleaning. So first, I'd like to show you Lancet, one of the top 2 medical journals. It says pollution causes 9 million premature deaths each year. And in some country, more than 1 in 4 deaths is due to pollution. Now, we have made use of the instrument I developed. First, identified that in the atmosphere, there are particles in 2 modes with a brick in here of 2.5 micron. Now, less than 2.5 micron is fine mode, and larger than 2.5 micron is coarse mode. And so here's the source and lifetime. So this is 2.5 micron. Less than 2.5 micron, they are caused by combustion, gas to particle conversion. So from chimney, from diesel engines, and so on. Now, these particles are so small that they don't settle very fast. So they have a lifetime of days to weeks and transport over thousands of kilometers. So people in Seoul, they like to say that some of the air pollution come from Beijing. It can be true because you can really transport this over a long distance. For larger than 2.5 microns is wind-blown dust, and then also resuspension from agricultural activity, construction, demolition. And these particles are quite big, so they settle very fast. And you see that the lifetime is only hours, so they rarely spread over 1 kilometer or 100 kilometers. So with that in mind, EPA set a PM 2.5 standard. Now you'll notice that 2.5 is in a subscript. That means PM 2.5 particle less than 2.5 micron subscript. And so the 24-hour standard is 35 microgram per cubic meter. Annual standard is 9 microgram per cubic meter. Now, EPA, if the city do not meet this annual standard, EPA can come in and then shut down some factory and so on. So this is very important. Now, I just want to also give you some magnitude in terms of particle mass, 9 microgram per cubic meter of air. Do you know that 1 cubic meter of air is 1.2 kilogram? And particle mass is microgram. So there's a billion times difference in weight. So we are talking about particle that weigh a little bit, but then it has profound effect on human health. So nowadays, there are filters development to remove the particulate matter emissions. However, there are volatile organic carbon, NOx, SO2 coming out. And upon irradiation by sunlight, UV light, it will turn it into ozone and secondary PM 2.5. So nowadays, in a lot of a big city, when they have a pollution alert, it's due to ozone because they are converted from gaseous emissions. So next, I'd like to address the topic of virus aerosol. Probably many of you still remember COVID-19. And now when you sneeze, do you know that you will have saliva droplet spraying out 100 micron size, which contain maybe 100 virus. It will accelerate at 100 kilometer per hour and stop about 1.5 meter away. That's why WHO suggests that you should stand 2 meters away from the infected person. And so what we like to do is to look at how virus can be transmitted. I taught this class with 125 students. You see that everybody is wearing a face mask. And then in the classroom, there are clean air coming out from the back and then return from the front. So we did a modeling of the aerosol concentration decay in classrooms. So in a classroom, there are air from outside going through a filter coming in. There's recirculating air for cooling the air, and then indoor air cleaner to recycle to get rid of the particles. And as a result of our modeling, we have put the modeling result on a website freely distributed to everybody. If you go to cfr.umn.edu, you will see this chart. Push the tab of particle decay model. You will see a chart and you can enter the flow rate of and the filter class of all the air cleaning devices, including indoor air cleaner. You put down classroom dimension, you put down number of occupant, and push a button, and you will have a curve coming out like this. Now, we find that under one of the condition, the air can be cleaned up in 13 minutes. Now, that's good because in the US, in between the classes, 15 minutes. So that means when the student leaves the room, before the next group of students coming in, the classroom will be clean. So many of the facility engineers make use of our model to look at different classrooms at the University of Minnesota. And they told me that U of M actually has a lower COVID infection rate than the other Big Ten university. So we hope that we did something good. And so we also evaluate at that time all the commercial respirators. Each curve represents one of the respirator. Now there are two differences. The blue shaded ones are electric media. That means the filter fiber has charge on it so that the charge will attract particle to be collected. And here, on the lower curve, those are mechanical filter. You see that the electric media has 3 times higher efficiency than the conventional media. And so my PhD student, Drew Thompson, he did a PhD thesis on electric filter media. First, he looked at the fiber collecting particles, and then mechanically. So you see that while small particles are collected with high efficiency because of diffusion, large particles, they decline. In fact, at 120 nanometer, that's the COVID-19 single particle size, efficiency is less than 20%. So he finds that by putting a charge on the fiber, the curve went way up. So you see now it goes from less than 20% to 80%. So with that, we were able to publish quite a few papers on that, and people know about it. And electric media are used quite a lot nowadays. Next, I want to show you the urban air cleaning. We have developed an indoor air cleaner, diesel engine filters, and solar-assisted large-scale air cleaning system, sources for cleaning up the urban city. And then the last one, we developed CO2 removal sources to clean up, mitigate the CO2 for climate change mitigation. So you agree that if we can do all of this well, we will create a sustainable environment for the world. So the WHO mentioned that 4.2 million deaths are caused by exposure to outdoor ambient air pollution. And in India, 1.67 million deaths per year due to air pollution. And so you see, this is taken at Delhi. You know that the 24 hours standard is 35 microgram per cubic meter. You are seeing almost 20 times higher air pollution in Delhi in this particular day. And so about 10 years ago, my student and I developed this concept of solar-assisted large-scale cleaning system. So we are modeling a glass tower. The perimeter of the glass panel can go for a kilometer. And so the glass panel near the center there's a tower, is in the center is higher, so that when the air heat up by solar energy, buoyancy will cause them to rise to the top. And so they tend to go to the center where we put a filter to remove all the particle, so only clean air come out. So we did this modeling using weather research forecasting model, which give you the global temperature, solar energy, those type of thing. And then we also use Fluent to calculate what's happening inside the tower. So this is assuming that we have 8 of this tower around the Beijing Basin. This is Beijing Basin. And then we use the WRF to model the flow and so on. We find out that in 2 days, the Beijing air pollution will drop by 15%. Now, of course, this will be a massive investment. So we are fortunate that there are several pilot scale made. The first one is in Xi'an, and the second one is in Yancheng Science Park. And then the third and the fourth one is in Delhi. And I will show you more detail. So this is the one in Xi'an. Here you can see that the glass panel is tilting upward towards the middle, so that when the solar energy hit the air below, the air rise and go towards the middle, and along the path, we put in filter system to remove the particle, so that only clean air come out from the top. Now this one has attracted a lot of people to visit, thousands of technologists. I just want to show you that our model is actually quite good. The red color indicate the simulation results, and blue color indicate actual measurement of the flow rate into the tower. You see very, very good agreement. However, there are 2 points on the north side of the tower. The airflow rate is quite a bit lower. Now, the reason is that the sun is always on the south side, so that the solar energy on the north side of the tower is decreased due to the shadow of the tower blocking some of the solar energy. So we were able to do this, and they did experimental measurement and agreeing with what we model. So guess what? A US magazine, Money magazine, in 2018, they published 28 incredible made in China innovation that are changing the world. The first one is moon landing, and our sources is number 22. So it's great that we are being acknowledged. And then these are the 2 set up in Delhi. Now in Delhi, one of the units is located between the hub, transportation hub, with train, with MTR, with bus depot. So every day there are hundreds of thousands of people around this area. So one of the units is placed there, and you see that we reverse the flow. In this case for Delhi, we use fan to blow the clean air out, so that the whole surrounding will be clean. Okay, so next, I'd like to address the health effects in both the harmful and beneficial applications. So now the landmark study is the Harvard 6-city study that is done during the 70s. And so they select 8 different city, medium-sized city, and measure their PM concentration, PM 2.5 concentration, as a function of death rate. And they put P, Portage, Wisconsin, as the with the mortality rate ratio of 1. So everything is comparing with the death rate in Wisconsin. You can see that from 10 to 30 microgram per cubic meter, the death rate increased by 30%. Now, there's a follow-up study in the 90s and showing that all the city has now reduced, now this is 90s, reduced PM concentration resulting in reduced death. Like here, we're just talking about from maybe 16 to 13, not that much change, but then the death rate decreased by 20%. So this works. So we really should try to reduce the concentration as much as possible. Now that's the reason that US EPA has reduced the PM 2.5 concentration standard to 9 microgram per cubic meter. So I should mention that all the city now met the EPA standard. So just imagine how many deaths are avoided due to this PM standard. Next, I want to talk about the technical nanoparticles. You know that carbon nanotubes are used in sports equipment and bicycle because they make the material quite flexible. And if you take a look at the electron microscope, you see that the carbon nanotube has a diameter of 90 nanometer and a length of 10 micron. And the asbestos fiber is 120 nanometer, length of the 2 micron. So the physical size looks very similar, and everybody knows that asbestos fiber causes lung cancer. So we collaborate with nanotoxicologist Gunther Oberdoster of University of Rochester, and he has an animal lab, and so here he put the 2 of the rats. Actually, the rats, I saw him taking out from the cage, and then they run around in the wheels, and then they put a couple drops of isoflurane, and then they sleep like a baby. And so sometimes when I cannot sleep at night, I'm thinking of that isoflurane. But anyway, this rats, he would stick a tube into their throat, and then this chamber has the pressure fluctuation helping them to breathe. And on top is our electrospray that we disperse the carbon nanotube into single particles to be breathed by the rats. Now, I should mention that for those of you knowing about the lung, our last stage, alveoli, is where the gas exchange takes place, oxygen coming in, taking out CO2. And for that, the cleaning mechanism are the macrophages, this type of cells. They will claw around and they see a particle, a known particle, they will swallow it. Now, guess what? The carbon nanotube is so long, they cannot swallow it completely. There's a tail sticking out. You see that sticking out from the membrane. And guess what? These are the carbon nanotube that retain in the lung for a long, long time because they are so long that they cannot be cleaned easily. And so if you look at asbestos fiber production in years, especially at the World War and after World War, the carbon nanotubes are used as a thermal insulation in ships and then at home. And then at the peak, people discover that there are people suffering from mesothelioma, which is a lung cancer. And what is not so good is that there's a long latency of 30 years. So although they stop producing carbon nanotube, but the lung cancer rate is still going up. So fortunately, the company have set up $30 billion of trust fund to compensate those victims. If somebody get mesothelioma due to carbon nanotube, they can go and get money from the trust fund, I believe $200,000 per case. So we did the initial study, and after that, there are studies in Japan and Europe that confirm that our finding. So NIOSH recommend an exposure limit of 1 microgram for carbon nanotubes. Now, previously, they treated that as just nuisance dust, 3.5 milligram per cubic meter for carbon black. No, you see that this is tightening it by 3,500 times. And one of the large company, it's a German company, decided to cancel production of carbon nanotube after developing the capacity of producing hundreds of tons of CNT, carbon nanotubes. This is a good thing. Just imagine how many people will die after 30 years if they continue to produce. So now, one of the reasons why nano size is so effective, both beneficial and harmful effect. If you look at the diameter ratio between the soccer ball and nanoparticle of 10 nanometer is 10 to the minus 8. The soccer ball to the Earth diameter is also 10 to the minus 8. So that means if you produce enough 10 nanometer nanoparticles and stuff the soccer ball, it's proportional to producing enough soccer ball to stuff the whole world. Just imagine how much surface area is being produced. So that's why, you know, all the chemistry is surface dependent. That's why they want to make size smaller and smaller to have better chemical reaction for good or for bad. And so my student and I, we develop a electrospray systems. Now, if you look at a nozzle dripping liquid, you have a large drop dropping out. Now, if you put a voltage on the nozzle and continue to increase the voltage, it will go into a Okay, so it will go into a cone jet, oscillating between cone jet and a rounded meniscus. And if you continue to increase to a higher voltage, it pops into a conical jet. Now the liquid come out from the tip of this conical jet. So you can imagine that particle coming out turn into nano-sized particle. And this two papers received 2,000 citations because we teach people how to do it. Now, one of the end result is that we have 12 U of M patents, and they have been licensed to a company, Nanocopier, and they are making a FDA-approved cancer drug right now. So we are doing something good with that and saving some life. And of course, all this air pollution control save a lot of lives too. This is what we want to do as engineer. Now, another technique that we haven't explored yet is to make the electrospray into a gin gun, because there's a very high voltage at the tip, so that the particle will accelerate at high velocity and shooting in the Petri dish where there are some cells. So we collaborate with Chris Wan. She's a pulmonary doctor, and she suggests that we shoot the enhanced green fluorescence protein from the jellyfish and into African green monkey cells. And so the high velocity will inject the genes into the cells, and if they combine with the nucleus, then you will see gene transfection. Now, if you put the sample of the Petri dish in the oven for 24 hours and bring it out, you see that the cells is lit up due to the fact that the green fluorescence from the jellyfish showing that transfection is successful. Now, next is a sensor that we have developed. In fact, the student that worked on this, Ryan Judici, is sitting in the back. Can you raise your hand? Yeah. So he's going to be here for 1 month. And so here we are shooting a laser into a box where we pass the aerosol through. And on top of it, we put in a camera to capture the image. Now the whole system costs maybe $200 to put together, or $300 maybe. And so you can see that when the laser beam hit the particle will scatter light at the same wavelength as the laser beam, and we call it the dynamic light scattering here. And on the other side of the chamber, we put in a filter to take out all the dynamic light scattering wavelength and measure only a long wavelength. Now, all the bioaerosol, they will, after irradiate by the laser beam, they will have induced fluorescence of a much longer wavelength. So if you look, the particle go from the right to the left, and then on the left, you only see the induced fluorescent peak. So we did some confirmation, and we have, on the left-hand side, we put in salt particle, and then this is elastic light scattering, and this is induced fluorescence. So you see that for salt particle, there's no signal at high wavelength. However, for the case of the bioaerosol, you see on the bottom induced fluorescence going off. And so the other thing we have done is to look at the color of the induced fluorescence to trying to identify what type of virus it is. And you will see that some of the particle has green and a blue color that indicate different type of bioaerosol. And also Ryan developed this low-cost aerosol concentrator because the bioaerosol comes in very limited low concentration. So we need to concentrate the bioaerosol concentration. This one that he developed can concentrate 400 times. So he used a 3D printer, 3D printing technique to build this unit, and it's working very well. He published a paper already. And one of the applications could be that we can mount this bioaerosol sensor on a hospital robot. It could be patrolling around the hospital, and if it detects COVID-19 or other virus aerosol, the top will pop out, and then there will be UVC laser, UVC light coming out and kill the bioaerosol around the unit. And so the UVC light is used because it's ozone-free, and also it doesn't penetrate human skin very much. So we are also doing this UVC biosafety study at U of M with one of the biotechnology professor. Now, finally, I'd like to talk about the last part, filtration. Here are a list of 18 companies that are supporting us, including 1 Japanese company, 2 Korean companies, 3 German companies, 4 Chinese companies, and the rest of it US company. And so one of the things we do is deep learning, using deep learning to obtain the efficiency of the membrane filter and fibrous filter. And so one thing neat about this is that if we use deep learning, we can just get 2D image of the fibers on the top and bottom or on the side. And what we did is to make use of machine learning, CNN technique, to model, and so we can take picture of the filter and get the desirable output efficiency, pore size, and all of that. And so the traditional technique is to use fluent technique to pass the aerosol through the filter, and then we have here 14,000 3D structure. And to do the traditional technique, it actually take 2 months of supercomputer to do it. However, with the machine learning technique, we can do it in a few seconds. So you see the V-shaped curve and the agreement between the traditional technique and our technique. And finally, I want to talk about the temperature rise over the ocean. You see that starting last year, the temperature is quite a bit higher than 35 years. And so when temperature rise, sea level rise, there will be hydrological extreme in droughts, floods, and fires. So health effect, heat stress, respiratory disease, malaria, cholera, large-scale migration. So health effect costs a lot of money, but then using technology, it can cost 10 times less. And so New York Times mentioned that Canada's wildfires is as much as Japan, the whole year of CO2. So in fact, last week in Minnesota, we have 200 microgram per cubic meter. You know, the 24-hour standard is 35. So we normally have 5 or 6 microgram per cubic meter. It's due to the wildfires coming from West Coast. You see that they really transport a long distance. So here we do laboratory study using a ring furnace and then a glass tube, putting in a wood stick, and then it will traverse across. And so we create wildfire lab data. And we also, in fall and spring, northern Minnesota, they have control burning of forest fire and grass fire. And we make use of drone to fly around, here's the drone, and capture the particle. Guess what? We find out that with the wildfires, particle is not at all like the regular aerosol particle, because wildfire particle has a lot of liquid condensables, and when it is deposited on the fiber, it will spread out and cover the whole fiber. That is, all the electrical charge on the fiber is concealed. So all in a sudden, the efficiency go from 80% down to less than 10%. Now, thing about firefighter, they think that they are well protected. And no, you know that this is the experimental data in the lab. This is a field measurement, all demonstrate that after you expose the filter for a few hours, efficiency can drop to 10%. So firefighter will be breathing 90% of the smoke into their lung. So on the second generation sources, it's making use of water spray to knock out the particle. But we can also put sodium hydroxide in the water and spray it. The sodium hydroxide droplet can take out the CO2. And so this is the technique that I like to promote next for our sources. And actually, American Physical Society, they publish this direct contact method too, but they use a fan to blow air to the tower, which drip the sodium hydroxide liquid. And in the end, they said that it's too expensive because you are trying to use electrical energy to blow the whole world's air into this farm. And but for us, we don't use any electricity. We use solar energy, so we make it possible. So I actually went to Saudi Arabia to talk about this technique. And so we can capture 30 million tons of CO2 per year. And Saudi Arabia goal is 44 million tons of CO2 per year by 2035. But if they take this technique, they can achieve that in 2 years. And so we can also install photovoltaic panel on part of the shroud. The electricity can be used for 7.2 million households. So this is what we are promoting. In fact, we just published a review paper that review 6 of our previous publication and proposed this. So in Saudi Arabia, I gave a talk at King Abdullah University. You probably see this president, the dean, and then these two are from TCL. TCL is a Chinese company that produces the world's second largest PV panel in the world. So in conclusion, nanoparticle technologies are multidisciplinary field with beneficial and harmful effects to the environment and human health and to semiconductor manufacturing. What we like to do is to perform fundamental and applied research to create a sustainable environment that will enable people and the environment to prosper together. Now, I think this one, I should just mention that I suggest to have academia, government, and industry collaborate and to solve the problem. Okay, with that, I'd like to conclude my talk, and I will be happy to answer any questions that you may have. Thank you.
Thank you very much, Professor PUI, for your, excellent, attractive, talk. So, and also I'm very impressed by your, great achievement, in many fields, microelectronics, air quality, health factor, and filtration. So, okay, so I think our audience, yeah, you see,
Okay.
and first question.
Okay.
Yeah, I can hear you.
Thank you, Professor PUI, for your informative talk. And I believe without a doubt, definitely you contribute a lot to the field. So right now, I'm Chen Shan, and right now I'm a student working in one of your directions. So just out of curiosity, I want to ask a few more details on your studies here. One is that I think for the classroom case, you presented a model platform. And I think based on the result, it seems like the decay curve, it looks like exponential model.
Yeah.
So I'm just curious what kind of model that is exactly, and how did you validate that model? And the second one, I think, is regarding for the animation you presented on the urban contaminant transport. I think that animation, the video looks pretty nice, but I'm just curious what kind of model or what kind of technique you used to predict that.
Yeah.
So
Thank you for
that's
your
all.
question. The first one, you talk about the classroom model. Now, we are using just traditional heating, ventilating, air conditioning model. This is well known, but what we did is that we were able to also include the real life situation and to put into the model. So yeah, we publish maybe 2 papers on that. Just take a look. Yeah, go to Google search with my name and classroom something. And with the sources modeling, I mentioned already, the weather condition is using weather research and a forecasting model. And then the inside the tower airflow, we make use of traditional fluid mechanics modeling. And we have published 6 papers on that. And recently, I was told that our review paper has been accepted by Journal of Environmental Sciences. So it will be coming out in the coming weeks. So you can take a look once it come out.
Okay, thank you.
Okay.
Thank you. Is there any? Okay. Oh, you go.
Oh, Professor Yuko Lee of Hong Kong U.
Yeah.
Thank you very much for Hong Chang.
No, not really. A very good talk. So maybe 2 questions. Number one, this fighters problem. So the particles became wet, and so that your mask reduce efficiency. So there must be some masks with what is called hydrophobicity, right? The surfaces can do something about it.
Yeah, that's what some of our CFR companies now working on, trying to overcome that. But this, we are the first one to demonstrate that. So we have written 2 papers that will be submitted in the coming month.
Oh,
so
wonderful.
Yeah.
So another general question maybe, because you have covered so much, and from the very beginning work for Intel, and then now to ocean warming and Canadian wildfire and so on. So how do you keep up with and machine learning, keep up with this new knowledge over the years?
We have 18 companies supporting us. So we always like to think of new topics to excite the company. So, and we are fearless to get into something that we don't know. This is what research is about, right? You don't predict what will happen. You just go into it. And it's good that our industry funding, they allow us, they review us and they suggest topics for us to do. And so we are thankful for those companies, yeah.
As always, I enjoy your talk a lot. It's really inspiring. In the very beginning, you talk about ozone interaction reaction to form the fine particles. So I just thinking, now the ozone level is actually getting higher and higher in atmosphere. Is there any way we can remove the ozone before it turns into a fine particle?
I'm collaborating with Ziyi Li of University of Science and Technology, Beijing. And he is really a very excellent group to look at absorption of all kind of gas absorption. So gas absorption, you can think of those molecules as particle too. So, and we collaborate in that, and he actually was able to put his technique into actual working model, working system. I should mention that he's a very young person, but then this year he received a Beijing Nova Award for his work. And previously, his previous director who retired now, he's the director, he developed a system to provide oxygens for the worker digging the tunnel to go to Xinjiang, at high elevation, long tunnel. Many workers die because suffering from fatigue and lack of oxygen. But for this group, they develop a technique to basically reject the nitrogen, take the air, reject the nitrogen, so the oxygen is concentrated, so the worker can breathe periodically. And for that project, the whole tunnel was completed without one casualty. So they receive one of the top award in China for doing that. So I introduced him to Boeing commercial airplane, at high altitude. There's a lot of ozone coming in too. So he's collaborating with Boeing to help to reduce the ozone in the aircraft, yeah.
Okay, thank you very much.
Questions from our audience? Oh, yes.
Hello, Professor Pui. Thanks very much for your presentation. I'm Wang Yu from Professor Guo Hai's group. I'm really interested about the air purifier tower. I'm just curious about, is it possible a huge air purifier can be movable? For example, if the wildfire happens, then the planes can take the many air purifier towers to go there, then to absorb the particles.
Yeah.
And for example, like the dust events happened in China, then we can move some purifier towers to solve this problem. Is that possible?
Good question. We have actually developed a mobile system and deploy it in Taiwan's science park, and it works. And then we disassemble it. And now it's not when you talk about the big unit, it's kilometer diameter. It's not something that is very movable. So we don't want to spend time doing that. But I do have you have a good question, because I do have one city close by Yancheng that they are trying to tear down an old district, and they worry about all the dust emission coming into expensive district. And so they asked me whether we can build the sources for them. I said, no. Why don't you just spray some water? Those are big particles. You can take care of them. Yeah. But somehow they want me to present it to the city of a big plan. I think it would be misuse of the money to use the sophisticated system. Just use water spray. Yeah. That's what I suggest to them.
Okay. Thank you for the answers. Okay.
Thank you very much, Professor Pugh. So my name is Wang Cuntong. My study is about bioaerosol transmission. So Actually, I have a question about the bioaerosol technology. So you mentioned that we can use fluorescence, the laser, so we can distinguish bioaerosols from the normal aerosols. So can this technology distinguish virus particle and bacteria particle? So maybe they are a little bit different.
Yes, that's why Ryan is here. Professor Shangdong Li, he did a lot of work with looking at wastewater plant. There's a lot of bacteria coming out. And so Ryan is looking into the possibility of using this sensor to detect bacteria. In fact, he would like to eventually also look at fungus. You know, for old building, if we turn on the air, you smell a lot of them because those fungus, they release maybe sporulate, and then you smell it. So this is part of his plan, yeah.
Okay, a following
his
question.
second year PhD student, and he will be writing 2 papers on this bioaerosol sensor this summer, yeah.
Okay, so a following question is about, so do you have a plan for the commercialize this technology so we can buy the related equipment for the pandemic measurement? So before we know there is a pandemic.
Yeah. We are talking to TSI that develop all our PM 2.5 measuring instrument. They're interested, so we talk about that. So we hope that, but I think that usually the company, they really want to see that you patent it, which we have 2 patents already, and also build it to the point that they can easily developed. So I think that might take another 1 or 2 years to complete. Yeah.
Okay, thank you.
Okay, yeah.
I don't need this one. Yes, for showcasing me the power of environmental engineering, saving our life, even saving our planet. Yes, I'm Guofeng from Professor Li Xiangdong's group. Yes, so I have a background from the health science, so I'm more concerned about the carbon nanotube CNTS you mentioned. So given its wide application potential, so how about the health risks? Like it has a similar effect with the nanofiber, the asbestos with lung cancer carcinogenic mechanisms. So this kind of thing. What's your viewpoint on this?
Yeah. The reason we do that study is that carbon nanotube is very new, and there are probably a lot of students using carbon nanotube in the lab, and we want to make sure that they don't breathe it and then develop cancer 30 years later. So that's why we do the study, and NIOSH now has strengthened the standard 3,500 times so that to protect the worker, yeah.
Thank you.
Okay.
Okay. Yeah, Professor Pui, I do have a question. I saw your presentation. So you mentioned some cities in the States actually already have the PM 2.5 level, like about 9 microgram per
So
liter.
actually,
How do they achieve?
all of them need to be below 9.
Right.
And actually, this new standard of 9 microgram was implemented last year, 2024. So, but then they have to evaluate the city for 3 years in a row. If for 3 years their annual average is greater than 9, then EPA can go in and shut down some factory.
Okay, so so it's very close actually to the WHO, the guideline, like
Yeah, so
5
so they
microgram per
keep
liter.
on trying to reduce the PM 2.5. Any particle is not good for you.
Right. So they mainly cut those the major sources to reduce this the PM 2.5 level.
Yeah. You know that PM 2.5 are from combustion activities.
Yes.
So you can shut down some power plant, implement a strict standard. Chinese city is in a better shape because you have a lot of electric car that
Yes.
help out a lot. Yeah.
Yes, thank you. Yeah,
It says 5 minutes left. So I'm happy that I leave enough time for questions.
yes, yeah. More questions, you know, you got opportunity. Yes.
Thanks very much, Professor Pugh, for your sharing. And I have a question about the solar associated large-scale cleaning system. You mentioned it can remove the air particles and of the air pollutants. And I'm curious about whether it can also remove the gas phase air pollutants like the ozone or VOCs in the air.
Yeah. So in fact, we are doing quite a bit of gas absorption study, first with Ziyi Li and now with Institute of Urban Development, IU Institute of Urban Environment in Xiamen. It's a Chinese Academy of Science Institute. And we are doing modeling. And so now we are trying to do more experiment. So it's on the way. Yeah. Gas absorption is going to be a next big topic for us at the Center for Filtration Research.
Thank you.
We don't develop quantum computer, by the way.
I'm quite curious about Ryan's project about detecting virus in the sewer system or the waste treatment plant, right? How is do that? What is the driving force of that virus in the sewer systems?
I don't connect between Ryan and the fire. Yeah.
The virus, is it detecting the virus in the
Virus. Yeah. Okay.
in the
Yeah.
wastewater treatment plants or
Yeah.
the
Yeah.
waste system?
So this is what we are questioning Professor Xiangdong Li, and he has a lot of experience with wastewater. We have zero experience. That's why he's coming here to learn.
I see.
Okay, so thank you very much for your questions. So we close this session.
To express our appreciation to your lecture, we prepare a small souvenirs for you. Yeah, I also like to thank all of you for being here today. It's been a great pleasure and to see many of you who are very much interested in this topic. It's very important, as Professor David Pugh has already demonstrated that. And I also want to thank all who ask questions to make this session very cheerful. And then this now seminar is adjourned. Thank you.